Hey everyone, my name is Daniel Dobaya, and this is my presentation on the sun and how it produces light and heat energy. First off, I'm going to talk about some of the characteristics of the sun. The sun is one of 100 billion G2 stars in our galaxy. It weighs about 1.99 times 10 to the 30 kilograms, which is about 99.8% of the mass in our entire solar system. The diameter of the sun is 1,390,000 kilometers. Temperature on the surface is about 5,800 Kelvin, which changes. And in the core, it's about 15,600,000 Kelvin. It's also made up of 70% hydrogen, 28% helium, and then less than 2% of different metals being caused and created by different nuclear reactions happening around the sun. I'm going to explain the structures of the sun, starting with the innermost part and then moving towards the outer layers. The sun's power comes from its core, which is the innermost part. The core is about 25% of its inner radius, and the temperature is about 15.6 million Kelvin and 250 billion atmospheres of pressure. It generates about 386 billion megawatts of power, and they're all produced by something called nuclear fusion. Nuclear fusion generates gamma rays that move out of the sun, and these gamma rays are continuously being absorbed and then re-emitted at lower temperatures, so when it finally reaches the outside layers, it's visible light. Like I stated in the slide before, nuclear fusion reactions are a process between lighter elements and then they combine together to form heavier elements. Elements with low atomic numbers like hydrogen produce substantial amounts of energy. It's called the proton-proton cycle. Nuclear fusion in a burning star involves the fusion of two hydrogen nuclei to form deuterium. It's the same type of reaction that happens in hydrogen bombs. The mass-to-energy conversion is described by Einstein's famous equation E equals mc squared. So in the sun's core, every second, about 700 million tons of hydrogen are being converted into 695 million tons of helium. And from that, 5 million tons of energy are being created in the form of gamma rays. After the gamma rays are emitted by the nuclear fusion reactions happening in the core, they move into the radiative layer of the sun. This layer takes up about 60% of the sun's radius, and it actually takes hundreds of thousands of years for energy to get through this layer. It takes so long for them to get through the radiative layer because they're constantly being interrupted, absorbed, and re-emitted. The density of the radiative layer goes from 20 grams per centimeters cubed to 0.2 grams per centimeters cubed, which is less than the density of water. So since these particles are so packed together and tight in that zone, it takes forever for the light to get through there because they're constantly bouncing off of different particles, even though they're moving at the speed of light. And the energy in the radiative core, or the radiative zone, is electromagnetic radiation. After the thousands or even millions of years of light being moved through the radiative layer, they finally reach the convection zone. The convection zone and the radiative zone are separated by a boundary called the Tachok line. Sorry if I didn't say that right. Energy moves differently in the convection zone. For the last 20% of the way going towards the surface, the heat and the energy are moving outward with like a swirling flow called a convection cell. It's similar to the way the water flows in a pot of boiling water. And the convection zone extends to a depth of about 200,000 kilometers into the sun. The top layer of the convection zone is called the photosphere, and this is where the light photons are actually created and you can see the visible light. After the convection zone, now we've reached the sun's outermost layers, like the chromosphere, the photosphere, and then the corona. These outer layers actually experience differential rotation. So at the equator of the surface, it actually rotates every 25.4 days. The surface rotates that much and that often because it's not a solid planet like Earth. It's kind of like in a gaseous state. The core is the only part of the sun that actually rotates as a solid body. The photosphere is the surface of the sun. The temperature is about 5,800 Kelvin, and it has sunspots that are actually cool sections that are about 3,800 Kelvin. The sunspots can be pretty large, get up to about 50,000 kilometers. And this is where the energy is actually released as light. So the photosphere is where the light gets off of the sun and starts traveling towards Earth. And since Earth is 92 million miles away, the light takes about 8 minutes to reach our eyes on Earth because it's traveling at the speed of light. And it's also the source of solar flares. Solar flares are bursts of fire that extend 100,000 plus miles above the sun's surface. They produce bursts of X-rays, ultraviolet radiation, and electromagnetic radiation, and also radio waves. The chromosphere is kind of the atmosphere that surrounds the photosphere. It emits a reddish glow as superheated hydrogen burns off of the sun. Only seen during solar eclipse because the photosphere is too bright. There's too many light rays coming at our eyes. The temperature rises from 6,000 degrees Celsius to about 20,000 degrees Celsius. And people call it the color sphere because of the reddish hue that comes off because of H-alpha emissions. The corona is the outermost layer of the sun's atmosphere and also probably the most interesting layer. It can only be seen during a solar eclipse, but I say it's the most interesting layer because it's mysteriously hotter than the photosphere of the sun's surface. It's at 3.5 million degrees Fahrenheit. Why the corona is hotter than the surface, it's a mystery to scientists today. There's a bunch of research and theories going on that suggest maybe tiny explosions, known as nanoflares, help increase the temperature by providing bursts of 18 million degrees Fahrenheit. Also, maybe giant super tornadoes that come off of the sun release a lot of heat into the corona, causing it to increase in temperature. But the real reason, scientists still to this day do not know. Now that we know where these light rays are generated from, we can talk about how they travel through space and reach our eyes on Earth. We already know that it takes about 8 minutes for the light rays to reach us on Earth, and the light particles travel through space in a relatively straight line. It's not until the particles hit our atmosphere that they start moving because of all the gas in our atmosphere and pollution. Looking at the sun is kind of like looking in the past because we know when the light enters that radiative layer, it takes hundreds of thousands of years for it to reach the outside. So the light rays that we're looking at right now were actually created hundreds of thousands of years ago. So in theory, if there was aliens out there in a galaxy far away looking at us with a telescope, they might even possibly right now just be seeing dinosaurs walking on the surface. And that's pretty crazy to think about. And because the vacuum of space, there is no friction or interruptions as the light waves travel, so they're not losing or dissipating any energy along the way. Not only does the sun release the light rays, but it also releases solar wind, which is actually heat energy. And the solar wind that the sun releases is the renewable energy source that we know as solar energy. It takes about 4 days to reach Earth, so it moves a little bit slower than the light rays because it's not traveling at the speed of light. The sun releases more solar energy every day than what the entire Earth uses in 1 year. And we're not even using all of it because 30% of the energy from the sun is reflected off the Earth. So we're only using 70% of the energy we're receiving. And our atmosphere traps the heat energy that the solar wind generates, and so that's what's keeping our Earth warm, is the atmosphere around us. And the sun's energy is released in every direction, so not just right at us, it's released in every direction, and when we receive it at the top of our atmosphere, the energy we receive is about 1,400 watts per meter squared. The solar spectrum, or solar radiation spectrum, is the spectrum of light that the sun releases. It's got 3 main regions: ultraviolet, visible light, and infrared light. and it extends from 0.29 micrometers of ultraviolet light to about 3.2 micrometers of infrared light waves. The visible light comes off the sun with a wavelength of 400 nanometers to about 700 nanometers, and as the light from the sun enters our atmosphere, it is interrupted by air particles and pollution, which causes the different colors of the sky. Also, sometimes if you're looking up the sky on a very cloudy day, you can see the sun rays bursting through some of the clouds, and that's because the other ones are being blocked by those thick clouds in the sky. The ultraviolet light is important because it releases vitamin D through the activation of ergosterol. Sorry if I said that word wrong. But however, as we all probably have gotten in our lives, too much UV light can be bad and it can give you a sunburn, which turns your skin red and causes a lot of irritation. These are just some of the websites that I use to gather my information, and thank you for listening to my presentation. I hope you learned something.